What's up, everybody? Today I'm going to introduce to you how you can rewrite a complex number in polar form. And we're going to see as the week moves along that when you have the polar form of a complex number, it can actually make operations between complex numbers a little easier to perform. Okay? So it's been a little while since we've looked at the complex plane. This takes us back into part A of the course. But you can see the complex plane on your screen here. Remember, it looks a lot like the regular rectangular coordinate plane, except instead of the x-axis, you now have the real axis, and instead of the y-axis, you now have the imaginary axis. Okay? So when I have a complex number in rectangular form, I can think of it, let's say it's the number z, and it has the form x plus yi. Well, I can think of x as just the real number piece and yi as the imaginary piece, right? So the goal here today is to be able to convert these into their corresponding polar form, all right? Now, it's pretty simple to do. We can just use the same conversions that we have been using to go from rectangular to polar form. X, we know, is equivalent to r cosine of theta, right? And then y is equivalent to r sine of theta. So right there gives you a polar form for the rectangular complex number. And what I want you to notice is that when you're in that form, both your real number part and your imaginary part, they have this GCF of r that can be factored out, okay? So it's very common that you actually see the complex number in polar form written with that r out in front like this. We have r multiplied by cosine of theta plus I sine of theta. R is often referred to in the polar form of a complex number as the modulus of the complex number. So you might see that word repeatedly throughout this week. Okay. Now, some stipulations that I want to make sure we don't skip over. When you write a complex number in polar form, you have to make sure that the r value is greater than or equal to 0. You don't want to express it negatively, and you want to make sure your angle measure is between 0 and 2 pi or 0 and 360 degrees. So keep those in mind. Okay? All right, so let's begin. We'll plot the complex number z equals 3 minus 3i in the complex plane, and we'll write an expression for it in its polar form. So the number's presented to me rectangularly. This is also sometimes referred to as standard form. Okay? So let's make sure we understand that. Rectangular or standard form. And really easy to plot it in the complex plane. So from the origin, you just need to move 3 units to the right on the real axis, and then 3 units down on the imaginary. So it's like you're plotting the point of 3, negative 3, right? Okay, now to get this in polar form, I need to find the r value, and I need to find the theta value associated with that point. So you can think of the right triangle that's associated with this point. Okay, so to get r, or the hypotenuse of that triangle, we can simply use x squared plus y squared equals r squared. So your x is this 3, and then your y is the negative 3. So that's going to lead me to 9 plus 9 equals r squared. Of course, r is going to be the square root of 18, or 3 radical 2. So remember, this is known as the modulus of the complex number. Okay. Now, to get theta, a couple ways you can do it here. The goal would be for you to not have to use a calculator if possible. So if you look at your right triangle, notice your side lengths are the same. They're both magnitude 3, right? So that tells me I'm working with a 45-degree angle here as the reference angle. That's not my actual angle, though. I want to express it in the positive direction, okay? So I'm going to say that theta is equal to 315 degrees here, okay? Now, let's say you didn't make that observation, then to do this by hand, then you could also find theta by using the inverse tangent function. You could just take inverse tangent of your y divided by your x. But understand sometimes that's not enough. In this case, that's going to yield a negative angle measure, so I'm going to have to add 360 to it to bring it within the interval 0 to 360. So you can double check me on that, but that should end up equaling 315 degrees. So just make sure theta is in the same quadrant as the complex number, okay? All right, so we're pretty much ready here. We can take the complex number z and now express it as our r value, or our modulus, of 3 radical 2 multiplied by the quantity cosine of 315 degrees plus I times the sine of 315 degrees. Okay? All right, now the nice thing about these, they're pretty easy to check if you've done it correctly or not. All you need to do is distribute that 3 radical 2 back through. And if you've done that correctly, 3 radical 2 times cosine of 315 should give you 3. And then 3 radical 2 times I sine of 315 should give you negative 3i. Okay, so it's pretty simple to check there. All right, now let's go in the other direction here. I want to write this complex number. It's expressed in polar form to start. I want to put it in rectangular form, and once I have that, then it should be a little easier maybe to plot it in the complex plane. Okay, so we'll just begin by finding cosine of 30 degrees and sine of 30 degrees. So you can draw, a reference triangle to help you out here. Okay, so z is going to equal 2 multiplied by the cosine of 30 is radical 3 over 2. Okay, I guess I shouldn't put a parenthesis there yet. Plus I multiplied by the sine of 30, which is 1/2. Okay, then we can distribute here that modulus of 2. So 2 multiplied by radical 3 over 2 is going to give you, of course, radical 3. And then 2 times I times 1/2 is just going to lead you to I. Okay. So there is our complex number in its rectangular form. And now we should be able to plot that. So the real number portion of it is radical 3, which is roughly 1.7, and then the imaginary part is 1. So you're going to move roughly 1.7 units to the right and 1 unit up. And there would be the position of z.